Okay, welcome guys. So we're gonna continue with the mm, what were we doing? Right. So we're gonna continue with data structures and algorithms. We were doing the sliding window technique, which we had completed. So I had explained the two concepts: the fixed size window and the variable size window. The next thing we're going to look at, the next technique that we're going to look at is the two pointers technique. Um, so, right, sliding window. Right. Um, right. Okay. Let me see if there are any binary subarray with some count number of nice subarrays, number of substrings. Maximum point you can obtain from cards. Okay. For this, just for this point, at this point, I'm not going to solve these right now. Um, I've understood the problem. I've understood the technique. I've solved two problems. I know they're not a lot, but I have been able to grasp the main idea, I believe. I'm gonna go to two pointers. This actually contains sliding window and two pointers combined. Right. Largest substring with at most k distinct characters, minimum window substring. These are all good questions. Okay, as you can see. Fine, we'll solve these four questions. I'll also check these out once we do the two pointers. So let's do the two pointers technique. So we're gonna do the two pointers. Just okay. So this two pointers technique is not something very different. I mean, it's not something very difficult. It's rather very easy to understand and implement, and we'll see how we can do that. Let's open up this two pointers technique. Let's start reading from here, and we'll try to see what it is about. Okay. Then I'll be doing the once I do this two pointers, and once I've solved two to three problems based on that, I'll do the stacks and queues. Right, I want to do stacks and queues. So it was above this. Okay, stacks and queues, recursion, linked list, and bit manipulation. I can do later. Okay. Okay. Fine. The main idea what I want to do right now is grasp the techniques, because these are very common techniques that you must know if you want to solve problems, right? And I mean, there are a lot of problems where I encounter these techniques and I have no idea how to use them, or maybe a little idea. So that's why I just want to strengthen these techniques and then I can move on. Okay. I just want to check one more thing. So cadence I've done two pointers, sliding window done, two pointer I'm doing, Dutch done, prefix sum I did yesterday, Morris travel. This is okay, this is something other. This is for binary, okay. Longest subarray with zero sum, binary search and answer I have to do. This is okay, I thought it was Moore voting, but binary search and answer I have to do. Okay. So I'm doing two pointers and sliding window I've done, right? Okay, cool. Then we'll move on to strings, dynamic DP search, and sorting graphs. Okay, cool. It's going to be interesting. Fine. Let's start with two pointers. So what does it say? Excuse me. Right. So two pointers is really an easy and effective technique that is typically used for two sum in sorted arrays. Closest two sum, three sum, four sum, trapping, rainwater, and many other popular interview questions. Given a sorted array, sorted in ascending. So given a sorted array, sorted in ascending order, and a target. Question is, so this is basically a question which is saying, given a sorted array and a target, find if there exists any pair of elements such that the sum is equal to the target, right? A very simple question, right? So the question is basically you have 10, you have 20, 30, and then you have 50, right? So you have to find, and you've been given a target, let us say 70, right? So this T represents the target, and this is 70. You have to find whether there are any two numbers, okay, any pair of elements, okay, I and j, such that the sum is equal to the target, right? The brute force approach to go for this, the brute force approach for this question would be to, this is the element I, right? You will stay at this element, and with every other element, 20, 30, and 50, you will check whether the sum is 70. Then you will move I, then you're going to move I to this point. You'll move I here, you'll check for every element, which is 30 and 50, you will check whether the sum is 70. It will be for this, right? And then you will check with 30 and 50 whether it is 70. So that is how this question will, that is how the brute force technique will look like. So basically you're going from 0 to all the way till all the elements, okay, and minus 1, where n minus 1 is not included actually, because you don't want to, you need a pair of elements, you don't have to come to the last element, and for every element you are traversing approximately n, so it will be, complexity will be, it will not be n squared completely, but it will be around n squared, because for this element you'll go all these elements, for this you're going this, right? So for 0 you go from 0 to last element, for 1 you go from 1 to, so it will approximately be close, approximately you can say it is n squared. That is the brute force approach, right? Right, as I said, the naive method is the brute force approach, which gives you a big O of n squared time complexity and a big O of 1 space complexity, which is simple. I can show you the implementation again. I'll actually show you the implementation again. I'll code it up for you. So we'll just do it here and we'll see. Okay, this is the sliding window sum, right? A I minus a minus b. Okay, I'll just create another function. So okay, I think okay, I'll code it up here, right? So I'm going to code the naive approach or the brute force approach first, just to show you guys how it works. Okay. So what we're going to do is we're going to just iterate. Okay. We have the target available for us. We're going to create a for loop. We'll say for integer I is 0, I is less than arr dot size. Okay. I can just create, or I can just say integer and arr dot size. Wait a second as well, right? And then I is less than n, I plus plus. For this will be integer j is equal to, starting from I, j is less than n and j plus plus. So the value of the sum, okay, we need to calculate integer sum, which will be array of I plus the array of j. Okay, so this will be actually I plus 1. One element. So why I plus 1? Because we're going to have, this is I plus 1. Okay, this whole thing will, so this, when this remains I, this is I plus 1, then this is I, then this is I plus 1, then this is I plus 1, like this, the I plus 1 moves on, right? So we calculate the sum, and we simply say if the sum is equal to the target, we can just simply we need to return the answers. Okay, for an answer, it is a boolean value. Okay, so it's a boolean value. Fine, it's a boolean value given an array, determine if there exists. So I just need to, we don't need to return anything, so we just say return true. Fine, right? We just say return true. If it comes out of the loop, we know that if this comes out of the loop, we need to return false. So this is how it works, right? And you can see that if we try to run this, it works perfectly. What I'll do is I'll also print the values that are there that are giving us the answer. If it is true, I'll also print the answers. So I'll just create a vector. Right, I'll just create a vector integer answer. Okay, I'll just create a vector integer answer and I'll simply say answer dot pushback. If the sum is equal to the target, answer dot pushback I, array of I, and answer dot uh I think I can do this. Array of I comma array of j, and I can say C out uh, answer of 0 and answer of 0 of 1. So this is going to be your values. These two are going to be your values. Okay, oh, I'm getting an error. What is the error? Mm, vector integer answer. I thought it is fine. Okay, okay. For that, I need to be this. Has to be to size 1, right? Okay, I'm getting an error. Wait a minute. Answer 0. Uh, okay. I'm sorry. It's not a 2D array, right? My bad. It's not a 2D array that I've created. So for that purpose, for that reason, it's not printed like this. Um, I'll have to say answer. I'll have to say I think it should be answer 0 dot first, like this. Answer 0 dot answer 0 dot second, maybe. Right. It should be like this. Either a pointer or a dot. I don't understand. Okay, I can simply say answer 0 or rather, right? Simply say answer 0. How am I getting an answer? How am I getting a vector integer answer of 1? Okay, this is should be a pair, man. This should be a okay. I'm not really good at this. Oh my god. Okay, how to create a vector pair? So this is basically vector pair integer v vector dot pushback. I think since I've declared something, so I cannot do this. And vector pair integer int answer dot pushback array of I, array of j. I don't think there's any errors. There are any errors over here. Okay, fine. I'll do it like this. Make underscore pair. Then I'll say array of I and array of I and then array of j. Probably the way I'm just printing this is wrong. Answer 0 should okay. How do you print it? I dot first and I dot second, right? Or how do I be? You cannot do that. How do I answer 3 out first Don't answer. Mm, okay, this is not printing the custom output actually. Why is it not printing the output? Come on, man. Come on. Okay. Why is it not printing the output? Um. Okay, fine. Never mind. I'll just submit this. Now, what I can do is I can submit this, but it won't work because this is a big O of n squared solution, right? They've written a brute force solution and it will not work. I cannot submit it because then I will lose the points over here, but this is how it is. I want to save it somewhere. I don't think there's there a need to save it somewhere. We can just look at the method that let us look at what they have done. So obviously, as I said, enter I0 is less than ni plus plus j is I plus 1. J is less than n. If array of I plus array of j is target, then return true. As simple as then. Otherwise, just return. If the loop does not break, which means the true is not returned, then return false, right? So this is the so that was the brute force approach, which is big O of n squared. Now the better approach is binary search and hashing. So they have the binary search and hashing approach. Okay. What is this? 2 point. Right. Okay, not the binary search. The better approach is to use the two-pointer technique. Now we'll actually look at what is this two-pointer technique. We're going to look at this two-pointer technique. Just do like this. Okay. The two-pointer technique is simple. The idea of this technique is to begin with two corners of the given array. We use two index variables, left and right, to traverse from both the corners. Initialize left as 0. So there are going to be two pointers, which is one is left and the other is so the one sorry. So there are going to be two pointers. One is left, which is going to represent the first index, that is 0, and the right pointer is going to be at the other end, which is going to be the n minus 1th index. Now we're going to run a loop while left is less than right. Now why are we doing left less than right? The reason being, when you okay, so when I do a dry run, I'll actually show you that. For now, just remember that the value of left is going to be less than the right. So this is actually the base condition to also you can say stop. Okay, because if you don't keep, you have to have some condition in order to stop, right? So this is going to be your base condition. Now do the following inside the loop. Compute the current sum, which is sum is equal to array left plus array right. If the sum equals the target, we have found a pair. Okay. If the sum is less than the target, move the left pointer to the right to increase the sum. If the sum is greater than the target, move the right pointer to the left to decrease the sum. Now this might seem a little bit confusing. What I'll do is I'll try to show you how this actually works. I'll take one of these. Okay, I'll actually take this example right here, and I'll show you by doing a dry run. Okay, show you by doing a dry run. So this is similarly white. Okay. So what this is saying is we're going to have two pointers. This is going to be the left pointer, and this is going to be the our right pointer. So the value of L is equal to 0 initially. The value of R, which is these basically represent left and right pointers. This is going to be n minus 1, which is the last index. Now let's say our target. What is the target? The target is equal to, let's say our target is 16, right? We have to check whether there exists a pair of values such that the value sums to be 16. What we are going to do is we're going to move these. We're going to now remember the array is sorted. Okay, that's the only reason why we are able to use this technique. Otherwise, we will see other scenarios, right? So what you do is you want a value of target 16. Earlier, if I if we remember, we were traveling, we were setting, we were actually fixing the first index, then traversing the whole array, and then checking with each and every other index whether the sum was possible or not. Now, rather than doing that, which was now that was also repetitive and just a lot of computations, rather than doing that, what we'll do is we'll start with these two values. We'll add these two values and we'll say, okay, the current sum is equal to 45 minus of 8, which is actually simply, this is going to be 37, right? So this sum is 45 minus 8, this is 37. Now 37 is much greater than 16. Now observe something. You need to observe that you have 37 right now and you need 16. Since this array is sorted, you probably need to move this right pointer over here. Okay, now why are we doing that? Such that, so that the value, because if I were to move this left pointer, the value would only increase. If this is right here at 45, if I move this right here, what would happen is it just basically becomes 46, 49, 51, 55. But we want to go to a lower value, right? So what we do is we move this. Okay, when we move this, what will happen is simply, okay, it's just, let me just select this. Okay, so when we move this, now this becomes 10 minus 8, which is actually, now this becomes a value which is smaller, right? 10 minus 8 is 2. 10 minus 8 is just a value of 2. What we want, 16. Now this is smaller. Now we'll move our left pointer. And when we move our left pointer, the value becomes 11. Still smaller, 14. Still smaller, 16. So yes, there exists a pair of values that have the sum as the target sum, which is 16. So your answer is going to be 6 and 10 if the values are asked. Okay, if the indices are asked, you can pass the indices, or if it is asked simply yes or no, then you can pass the value answer as true, right? So this is how you actually perform this two pointer operation. Okay, a simple and efficient technique, right? A simple but efficient technique. Now the time complexity, since we're just traversing, the time complexity is simply big O of n. We're not using any extra space. So the space complexity is going to be big O of 1. Okay. Now we can actually code it up. Let's try to code this up. Okay, let's try to actually code this up. Just a minute, I'll just copy this somewhere. Okay, let's try to code this up. So initially we have a value of, we have 2 pointers which are L and R. Okay, the left and the right pointer, I'll write the value of n as array.size. Okay, now L is 0, R is n minus 1. Fine. Now while the value of L, because obviously now imagine this, we don't want the value of L to go past this, right? We don't want the value of L to even come to R, because if L and R collide, or you say L passes R, it means that we have already traversed the whole array. We don't want to do it. We don't want to do a repetition. If you just imagine L being here, this would do 45. But we don't even need to go there. There's no reason to move to 45 plus 10, 55. There's no reason to move to 55. So that's the reason we just say the value of L is less than R. Okay? The value of L is less than R, which are the pointers. We say this. We can say integer sum is equal to array of L plus the value of array of R. Okay. We can check if the value of the sum is equal to the target. We can just simply return true. Okay. Else if the value of sum is, let's say, greater than the target. Okay, so the sum is greater than the target, which is 37 is greater than 16. We need to move the which pointer needs to be moved? The right pointer needs to be moved. Okay, so the right pointer is moved. So we say r minus minus l, simply say l plus plus. Okay, simply we say l plus plus, and in the end, what we say is otherwise. If you just it's if we don't break out of the loop, then we just simply say false. Okay, so compile and run. Um. Okay, wait. Okay. This is if the value of sum becomes greater than the target. So if the sum is equal to target, while L is less than R, so it is the sum is equal to array L plus array of R. Okay. If the value of sum becomes target, return true. Else if the value of sum is greater than the target, the value of sum is greater than the target. So 37 is greater than 16, then we'll move R. So R is moved. R minus minus and R minus minus. Um, okay, the values are not sorted. The values are not sorted over here. Okay, so I'm just gonna sort the array because it's not sorted. You can see it works, and if I submit, you can see it passes. The time complexity, I think it's wrong to say time complexity is big of n because it needs to be sorted. If it is not sorted, then the time complexity is actually big of n log of n, but it's not. At least it's not big of n squared. Sorting, I think sorting takes sort time complexity for C++. It's n log n, right? It is n log n, obviously, right? Fine. Right. So we have this. So I've already told you how this works, right? So it is 8 minus of 8. So initially it is like this. You have minus an 845, which is 37, target is 16. So we move the right pointer, then the left pointer, then the right pointer, then the left pointer, and we get the result, right? So it is a left is 0, right is arrow dot size minus 1, left is less than right. Sum is the sum of both the values at left and right pointers. If the sum is target, return true. Otherwise, if the sum is less than target, move the left pointer. If the sum is greater than target, move the right pointer. Else, return false, right? Time complexity is big O of n and the space complexity is big O of 1. Okay. Now, the intuition behind it, if you think about why does this work, it's because we are always ensuring that if we have a greater sum available, we are not if we have a greater sum, let's say we have a sum of 37, we're ensuring that we do not move to a point that is greater. We want a value of 16, so we don't miss any smaller values, right? So we move this L pointer, we move this left position. We know obviously that by staying at this position, we obviously know that by staying at this position, this is 45, this is minus 8, which is obviously it's not possible that it will give me a value of 16. So since it is a really large value, I know that I need to move this. But you must be thinking, what if the value of minus 8? You already know that if this is minus 8, you will not have minus of 15 over here, right? It's not possible. If you're thinking, I know you might have had a question like, okay, this is minus 8. I could have had minus 15 or even a greater value that might have given me a value of 16. But remember that this is a sorted array. So if you were to have minus 15, it would not be over here, but it would be somewhere over here to the left of minus 8. So that is the reason we never miss a pair, because we ensure that we're moving in the right direction, right? Now there are some problems. Now these are some problems based on two pointers technique. Okay, two pointers. I can save this into two pointers. Right. We will solve another question based on two pointers. Let us solve another question based on two pointers. Find the closest pair. So find the pair in array whose sum is closest to x. Find all triplets with zero sum. Find a triplet with sum to a given value. Find a triplet such that sum find for elements trapping rainwater. Okay, what is this trapping rainwater? I don't. Okay, so this is find the closest triplet. Okay, might as well find questions somewhere else. Find a triplet with sum to a given value. A triplet. A triplet. Sorting into pointer approach. Proof of n squared. Now, this is a similar question, but the problem here is that we need to have we need to have three values, right? Instead of just one value, we have three values that we need to sum to have the given target, right? Okay. We'll take a 5 minute break and then we'll continue. So now what I'm thinking of doing is let's first tackle these two problems, which is triplets sum in an array and then triplets with zero sum. We'll do these two problems, and then after we do these two problems, I'm gonna probably head over to um, longest substring without repeating characters. Is it a hard problem? Is it a hard? It's a medium problem. It's a medium problem. Longest substring without repeating characters. It's going to be interesting. I will try to do these. I'll try to do as many as I can. Okay. Okay. If this is hard one, minimum window subsequence. Okay, it's not possible to do this minimum window subsequence. Maybe I can find it on GFG minimum window subsequence. So I can find it on minimum window substring subsequence. There was a similar question to this, right? That was minimum window substring. That was also okay. Wait, there was a similar question to this one. I think it was in sliding window, right? Minimum window subsequence and substring are different. What is this asking? Given two strings of S and T, return the minimum window substring of such that every character in T, including duplicates, is included in the window. If there is no such substring, the test case will generate answer is unique. Bank. Okay. Minimum window substring. We'll do a hard problem. I've already done this, man. Already done this. Subarray with k different integers. Okay. I'm gonna finish my topics first. So what I'm gonna do is I'm gonna do these three first, these two problems for the two pointers. Then I'm going to go to, because I've already solved a lot of these problems. What I'm gonna do is I'm gonna start. We're gonna start with stacks and queues because I really want to complete stacks and queues today. And then after I'm done with stacks and queues, uh, I think yeah, that's all I'm gonna do today. Right. Let's start with the problem. Let's start. Let's see what is this problem involving. Right. Where is this? Yep, this one. Triplets in an array. Right. So this problem right here. Question is simple. Determine if there exists a triplet in the array whose sum equals the given target. Return true if such a triplet exists. Otherwise, return false. Right. So what we can do is let's see 1, 4, 45, 6, 10, and 8. What is a brute force approach? What is the brute force approach? Let's see what is the brute force approach first. We have to find three values such that the sum is equal to the given target. Okay. Right. So for this, what we can do is brute force way. Now, the solution for brute force is going to be very complex because we're going to be using three nested for loops, and it is going to be of the form big O of n cube. You'll have I, you'll have a j. Okay, you'll fix I, you'll fix j, and then if I were to write the pseudocode, for example, right, I'll show you. I'll write the pseudocode. So this was the pseudocode. So for I from 0 to all the way till n, and then you'll have for j is equal to I plus 1 all the way till n, and then you'll have another pointer ij, and you can call this k is equal to j plus 1 and all the way till n. Now why is that? Because you're going to fix 1, okay, and then you're going to traverse 4 with 4. So 1 is going to be fixed, 4 is going to be fixed, and then you're going to traverse and then add the value 45, 6, 10, and 8. Then you're going to remove 4, right? Then you're going to move actually this pointer right here. The value j, I mean the value j, the variable j is going to be here. So then the value of k will start from 6. So because we've already considered 4 and 45, now it will be 45 and we'll consider 6, 10, and 8. Then it will move over here. Then we'll have 6 and 10 and 8, right? So that is how it will move on. You getting my point? So that is why, so that is the reason why the time complexity is going to be of the form of the order of big O of n cube, which is really, really complex, right? We don't want a complexity that high. For big O of n cube to run, you would need a constraints to be of the order 100 or just like 200, even 300. But the constraints here, as I probably know, it's 10 raised to the power 5 spaces there. So for 10 raised to the power 5, you probably need a solution that works. For 10 raised to the power 5, you need a solution that works in either n log n or big O of n, of the order of n log n or n. Okay. For higher than that, we require log n. This is just an additional information I'm telling you guys. For higher than 10 raised to the power 5, probably 10 raised to the power order 9, you need big O of log n or big O of 1. In this case, even this is low, then you need big O of 1, which is constant time. Just an additional information, right? Okay. All right. So that was a brute force, right? Now, what is a better way to do this? So, what is actually a better way to do this? Right? What is actually a better way to do this? If you look at the right, what is a better way to do this? A better way to do this would be to take the right. So since obviously we're talking about pointers, let's try to think of something in the terms of that. Right? Let's try to think of something in terms of pointers. Can we use 3 pointers? Right? Can we use 3 pointers to handle that? Right? But in that, even if in case we try to do that, right, we'll have to sort the values first. So that would be 1, 4, 6, 8, 10, and 45. Right? If I have a pointer over here, if I have a pointer over here, right? Okay, this is a little bit tricky. How are we going to move, right? Now the question is, how are we actually going to move? How are we actually going to move? Hmm. Okay. Problem is, how are we going to, right? How do we manage 3 pointers? So I don't. Nothing comes to my mind right now. Nothing is actually coming to my mind. How can we approach this problem? Hmm, okay. Okay. So probably what we can do is we can try to. Does it help if we try to create another pointer? Because what will this pointer actually do, right? What will this pointer actually do? What will it do? What will this pointer actually do? Right. So, okay. So if you try to think about something, right? Let's just go along with this. Let's say we have this, and we try to move this. So what is the current sum? It is 45 and one. Let's say okay. What is the required target is 13. Let's say we have 45 plus one is 46, right? Very high. Plus four is even higher. Okay. I something that comes to my mind. What I'm actually thinking is, is basically what if we tried to just calculate this and then checked if the other value exists in the array, right? So what if, for example, if I have 45 and 1, I count that 45 and 1 is 46, right? So what we do is we just move this. 45 and 4 is, wait a minute, what do we want, right? 40, I mean, 45 and 1 is high, 46. So we'll move this. So 10 plus 1 is 11. And we need a value of 2. Does that value of 2 exist in the array? It does not, right? Does the value of 2 exist in the array? It does not. So fine, we'll just say, okay, if 10 is really less, then we'll move this. So we move this. We have 14 now, and we are again one extra. So we'll move this now. We'll say, okay, we'll move this. Do we have a value of 1 available? We'll say, okay, we do, which means, okay, fine, we have a value. So we can actually create that sum, and that sum would be using 8 plus 4, which is actually 12, and plus 1 is 13, right? So you understand, we'll be using two pointers, but for the third value, we'll be actually creating we can say you can create a hash map, right? So you can basically create a map and then store the values in that. You can create a map and store the values, right? So you can basically create a map and store the frequencies maybe, right? So you can, as you go through the values, you can store the frequencies. Yeah, I'm thinking, what if a duplicate value is there? Because what if we need a value of 8, but we already are on the 8? We cannot double count the value of it. How do we avoid those cases where we are double counting the values, right? So for that, what we'll do is we'll only insert values when we have crossed them, right? We'll only insert the values when we've crossed them. Let's try to code this up. Okay. The time complexity, as a matter of fact, would be, since we are first we'll have to sort, which is big O of n log n, which is big n log n, and then we'll have to use two pointers technique, which is big O of n, and then for searching this up again, it will take the lookup, I think, is again n log n. Lookup for, if I'm not wrong, for uh, count, um, sorry, find in map, right? In map C plus time complexity. Find in map C++, the time is n logarithmic of n, right? So the time complexity for a map find function is logarithmic of n. So yeah, let's try to do this. Let's create L is equal to 0. Let's create R is equal to n minus 1. Initially we'll have 20 n is equal to size while the value well is less than R. Say sum is equal to R of R. Now the integer, we'll call it a required value. Okay, we'll call it required value, and that will be equal to target minus sum. Now we'll say, okay, if the value will create, we'll create a map. We can create an unordered map just to save some time complexity. We can create an unordered map. Um, and I can save the value of the find. I have to see how to use this function. So you can say mp.find key. Okay, I can simply say mp.find. I can use the key which is actually required. If this is not equal to not equal to mp.end, then what we can do is I hope I'm using this right, correct? Mp.find key to is not equal to mp.end, right? So this actually what this means is the value is found, because this is how the function actually works. Find function returns a value. If the value does not exist, it just returns the last pointer. It just returns the iterator. So the find function will actually return an iterator to the last value, not the last value. The last value. If the value does not return in from the map, right? So if the value, so now this means that if the value is present, actually, what we can say is I'll just return true, right? I'll just return true because I know that the value has been found. Okay. Otherwise, if this does not match, then I'm just going to add the value. So mp of I'm going to add what value I'm saying. Now, what value am I talking about adding? I'm saying I'll add mp of, let's see. So I was saying, for example, if I have one, right? If I have four, for example, if I'm at 45, if I'm at one, I'll move this 10, and then 1, 10 and 1 is 11, which is low. So 45 and 1. So I'll add 45. Okay. Right. I need to say if the value of sum is greater than the target, right? Let's just say if the sum value is greater than the target. There's no use in doing this if the value of sum is greater than the target, right? The value of sum is already greater than the target. We know that we need to say r minus minus, and this time I'll be adding mp of r plus plus. Okay, mp of a of r actually because we want the value to be added. Otherwise, if the value is otherwise, else if sum is less than the target, not even equal to, but the sum value is sum is less than the target, then we're going to say and mp dot find required is not equal to mp dot end, then return true. Okay, this is to be only calculated if the value obviously return true. Otherwise, if now otherwise what can happen, which means that the value is not greater. Okay, it's less than the target. For example, we have a value at 10, we have another value at 1, but the value is smaller. Okay, but we did not find, for example, 10 and 1 is 10 and 1 is 11, but we did not find 2. So what I'm going to do is, since I'm going to move from here, I'm going to add the left value. I'm going to say ARR of L plus plus. Okay, and I'm not going to add unless empty of ARR of L plus plus. Okay. Now I think that should do the work. Otherwise, we just return false. Okay, I need to sort. Begin. Uh, what is this saying? So this is this. If I think I've written the correct code. Sum is this required sum target r minus minus. Um, mm, as if sum is less than target and we don't find it, but it's not a plus plus return. I don't understand what is the problem. What is this? Expected this before token. Okay, sorry, I missed this. Missed a semicolon. Hope this works. Okay, so this returns true. Oh my god. Time limit exceeded. You can see it exceeded. Okay. It exceeded. I don't know why it exceeded. Probably some reasons. I don't know. It is some is now what is happening. Let's see. For example, let's try to run this code on this example right here. So initially the sum, so L is L and R are there. Initially the value is, I have not even created a sum. Or have I? I have, right? Okay, fine. So the sum is equal to array L plus array R, which is initially, which is the value of 8 and 1 9. Not 45 and 146. Then we say 45 and 146. We see that the sum is greater than the target. We see that the value is, we see that the sum is greater than the target. Okay, and we say R minus minus. Sum is greater than the target, so R minus minus, the value comes to, pointer comes to 10 and MP of array of R, which is, oh my god, this is to be done at this point before you move on. Before you move on. And then, oh my god, I've not even done L plus. Right, so that's why it exceeded the time limit. It did work, however, I have some confusion whether it's going to work or not. Hopefully it works. Okay, please work, please work. Okay, it did not work. Oh my god. Okay, let's see what went wrong. Probably it has a repeated value. I can tell you it has a repeated value. 98, 85, 48, 56, 65, 67, 90. Oh my god. How did I not actually, how did it not work for this one? Why did it? Question is, why did it not work for this? Let's see. So we basically say, okay, that initially we have LNR, right? So I'll just do it quickly, right? So we'll say, okay, the initially the values are at, okay, I need to create a sorted array first. The value, least value is 48. Least value is 48. Okay. Second least values are just two like this so that I know, okay, I've marked it. Next is 56. Then you have 65, 65, 67. Then you have 85, 91, and then 98, right? Okay. So initially the value pointers are at these points. Okay. So we say, okay, 48 plus 98, the target is actually 206. Target is 206. Okay. I don't know why is it not working. Okay, 206. Fine. Now 48 and 98 actually is 40 and 90 is 130 and 140, 146. So 146 is obviously low. So we'll say, okay, fine. If that is the case, we're going to calculate required is going to target minus sum, which is 206 minus 146, which is actually 60, right? Now, do we have a 60 present? No, we do not have a 60 present. So what we're going to do is we're going to add We do not have a 60 present, and which we know that the value is fine. This value is fine. We need a higher value. We're going to go to, we know that this value is fine. Since we have to 146, we need a higher value. We'll just move this right here. So we'll move this. We have 56. Okay. And what we do is we add 48 in case we need it, in case we need it in the future. But wait, why would we need that in the future? If we needed 48, it is already present, no? I mean, we're adding 98 and 48, remember, right? Are you getting my point? If I add 98 and 48, it gives me 206. If the difference of them was to be present in the map, in the map, okay, remember in the map we're talking, which is not, obviously, and by that's why I've added it later. So 48 has been added to the map, L has been incremented. And now we add 98 and 56, which is actually 98, 1950 is 140 and 140 and 14, which is 154. 206 minus 154 will be just simply 52. Is 52 present? No. We add 56 to the map and then we move on. 98 and 65. 90 and 60 is 150 and 163. And then 206. 3 and then 4. 43. Is 43 present? No. 67 and 98. 150 and 15, 165 and 206. 1 and 41 is 41 present. No. We're going to move on. 98 and 85. 170 and 13. 183 and 206. Is 23 present? No. 98 and 91. 199. We're out of options already. I don't know. You're saying true. So you're saying 206 is possible here? Using three numbers, 206 is actually possible. I don't see that. I don't see that happening. 206. Come on, where is it? 206. 48, 56, 65, 67. I don't see anything. Did we ever add 48 and 91? Did we ever try to add 48 and 91? Why? Because we thought, okay, it's already less. 139. What about this value? 5 and this is 16. This becomes 9. 9 and 7 is 16. And this will become 67. Oh my god, okay. 48, 67, and 91 work. I don't know how, but they work, right? So they work, but we're not even considering them. So this is a wrong idea. Okay, so this is a wrong idea that I had. Okay. I thought it should have worked. Let's look at the answer. How is it done? I'm not able to understand this. Obviously, the naive approach is to calculate the triplets, which is big O of n cube and big O of 1 bit, using the three nested for loops: I is 0, I is I said, j is I plus 1, and k is j plus 1. As I said. Simple naive approach using big O of n cube. The better approach is hash set. The idea is to traverse every element in a loop. For every AI, using the hash hashing based solution of two sum problem to check if there is a pair with sum equal to the given sum minus array I. Below is the step by step. If you've done the sum two sum problem, you would know that in the two sum problem we create a set hash, we create a set, and then we try to actually compute whether the value is present or not. And that's what I actually tried to do here as well, but it did not seem to work out. Okay, so iterate through the array, fixing the first element. For each array AI, each index, use a hash set to store potential second elements and run another loop to inside it for j from I plus 1 to n minus 1 inside the nested loop. Check if given sum minus array I minus array j is present in the hash set. If yes, then print the triplet, otherwise return false. So for example, I 0 is less than n minus 2 I plus plus unordered set integer st hash set integer j is I plus 1. So fix the third element as array aj. For j is I plus 1, j is less than n j plus plus. Now we're improving from big of n cube to big of n squared. And the second is equal to target minus array I minus array j. Search for second element in the hash set st dot find second is not equal to st dot end, return true. Otherwise st dot insert array j as a potential second element. Right, so you understand what we are trying to do is, I'll explain it to you. We're simply traversing, right? We're simply traversing and there's no need for sorting in this case. Okay, it's a big O of n squared solution. Okay. Right, I'll tell you what we are trying to do. Let's say we have this. Let's say we have this. What we do is we start with the value of I as 0. So I is at 1, right? The value of I will be at 1. Then we'll create a set and we'll set the value of j as I plus 1. We'll set the value of j, which is the next index. And for j is equal to this index till the very last index. Okay, I believe the very last index. We'll iterate, we'll calculate whether a value of target minus these two values, the I1 which is fixed and the j which is not fixed. So it will have 1 plus 4, 1 plus 45, 1 plus 6, 1 plus 10, 1 plus 8. And this sum will be subtracted from the target. Okay. So we do that and we check whether the value which is required is present in the set or not. If it is not present, we will insert 4. Now, because let us say we are at I, right? We say we are at I, and the result is something like, let's say, the result is I, let's say. The result is, I mean, we are at I, and let's say the answer is actually 1 plus 45. So when we are at 1 and 6, because when we were at 1 and 4, we knew 1 and 4 is equal to 5, and what we need is 6. But 6 is actually, now why are we inserting? If you are unable to understand why are we inserting at this point here, we do not have a set. Okay, we cannot insert. Now why are we not inserting all the elements? Why, you might be thinking, okay, we can just insert all the elements initially and then check if the set contains that value. Yes, but you will be reading all the duplicate values. You will be counting all the values twice. Okay, so in that case, if you were to have just a single value of 1 and you have, and let's say a single value of 6, and you might think, okay, 6 is present. Your value of j might be at 6 itself, and you might, and then when you need a value of 6, the required value is also 6. You find 6 and you say, okay, 6 is present. That means I have a value of 166, which is, let's say if your target was 13, then you would say 13 is present. But that is not true because there is a single 6 present, not two sixes. So that is the reason you cannot create the set initially. But only you will, so when you are at J, so you will, and as I was explaining, you are at I fixed, J is there, you will insert the value. If the value of, let's say, okay, let's say 13 is the only, 13 is the target. In that case, 1 plus 4 is 5. Right? So the value of 1 plus 4 is 5. And right, so 13 minus 5 becomes 8. Okay, cool. That is also true. We need a value of 8. The set is empty right now. The set is empty right now. As I said, I already told you the reason why we cannot store all the elements initially. And we need 8, but 8 is not present. 8 is empty here. Okay, 8 is not present here. We'll move our J. Okay, and imagine that when you're moving J, imagine that you're moving the value of J. Your J reaches this point 8. So when you reach this point of 8, and then you need a value of 4, and then if you're not inserting any values, you'll still not be able to write. You need a way to count 4. You need to know that if 4 is present. So that's why when you were at 4, you would have inserted 4, and then now you can know that your set contains a value of 4. Voila, you have got the 4, you have the 8, and you have the 1, which gives you a value of 13. Right? So that is the reason you'll start your value of index at 0. You'll, for all the indices, you will move I. Okay, then you'll create a hash based hash set. Okay, so you fix your I value, you create a hash set, and then you will fix your J, and then iterate, and then if you calculate the required value, so you calculate the required value by subtracting the sum of these two values of array I and array J by subtracting from the target. If the required value is present in the set, you return true. Otherwise, you insert the value array J into the set and then keep moving on until you find the value, and then outside the loop you just simply return false. So this is how the outside the loop you just simply return false. That is how the algorithm actually works. This will work in big, since we're having obviously two nested for loops, this will work in big O of n squared. There is no sorting, so it's simply big O of n squared. And the time complexity, the space complexity here is big O of n because we're using a hash set. Okay, this is a better approach than the previous one, which was big O of n cube, which was 3 nested for loops. But again, we can optimize the space by using just big O of 1 space. Okay, now we're actually going to use the two-pointer problem. How do we do that? Simple. Now this time we'll have to sort the values, obviously. We will fix the first element as the array I. So for it, I0 is less than n minus 2 I plus plus. Initialize the left and right pointers with start and end of the remaining. Initialize left and right pointers with start and end of remaining subarray. L is equal to I plus 1. R is equal to n minus 1. Okay. You fix, okay, so now I understand what they're doing. So they will fix this I, and the rest of the subarray is taken as the two pointers approach. So you'll have you will have your L pointer here. You will have your R pointer over here. And then you will run then you will actually perform in this subarray, right? You fix your I, and in this subarray, you're actually performing your two pointer problem to find the required two values after this. You might be thinking, what if I take I is equal to 4? How is the subarray going to be implemented in that case, right? Might be thinking about that. So L is equal to I plus 1, but L is always I plus 1 and R minus 1. You will, because we have already considered all the values with 1. We've already considered all the values with 1, so there is no reason to be having 1 again. When we are at 4, we will only consider this subarray. When we are at 45, we'll only consider this subarray, and this is the last we'll go because we need at least 3, and this is the last point we'll go because we need at least 3 subarrays. So you will see that I is less than definitely n minus 2, right? So this is now this is using two pointers. The time complexity is again big of n squared because of the for loop and the while loop, but the space complexity is optimized because it is the space complexity has been optimized because it is big of one. A great question, I believe. Three sum. Okay. Okay. So right, you have three. Actually, you have three. Right. I hope you've understood the approach of the problem. That there are three approaches: the brute force, hash set solution, the brute force solution. Then you have the map solution, hash set solution, and then you have the two pointer approach. Right. Okay. Good question. Good question. I'll do this afterwards. Then there is another one which is find all triplets with zero sum. Now this is again you might okay. Now this is all triplets with zero sum. Okay, this is it's similar, right? You just have to find three values with the value of target is equal to zero, right? The only thing changes here is you need a value where target is zero. Big of n squared time and big of n squared space. N square space. Why is that? Find all triplets with zero sum. Okay, the question is task is to find all the possible, not return true or false, but all possible indices such that their sum is equal to zero, and then return the values. Okay, that's heavy. That's some heavy stuff. We don't need to do that. The only question I need to do this is triplet sum in an array. Okay. Um, I'll make sure I do that. Make sure I do that question. And then I think we can move to stacks and queues now after a 5 minute break. Thank you guys for joining in. I'll be ending the stream.